Hello, my name is Alexander Reske, and I present Imitation Learning from MPC for Quadrupedal Multi-Gait Control, which continues our previous work on MPC-Net. Using Model Predictive Control on hardware requires that a new motion plan can be generated sufficiently fast, which can be difficult in complex MPC scenarios. This issue can be addressed with MPC-Net, which is an imitation learning approach guided by MPC and allows us to learn a control policy that can be evaluated quickly online independent of the difficulty of the control task. For this work, the main motivation was to use and extend MPC-Net in order to train a single policy that can imitate multiple gaits, such as trot and static walk. Specifically, we want to learn a policy that takes user-defined gait and reference commands and replaces its MPC teacher for the computation of the control input. First, I would like to give you a brief overview of our MPC setup. For MPC, we repeatedly solve the following optimal control problem, where we want to minimize the cost 1 subject to the constraints 2. For animal, we use a kinodynamic model, so the state consists of the robot's pose and twist, as well as joint positions, and the inputs are the foot contact forces and joint velocities. Constraints that we consider are, for example, that the feet should have zero contact forces during swing motions and zero velocity when in contact. To solve the OC problem, we use a sequential linear quadratic algorithm from the optimal control for switched systems toolbox. The equality constraints G are handled using Lagrange multipliers nu, and the inequality constraints H are considered through a barrier function B. The differential dynamic programming-based SLQ solver provides a linear feedback policy pi MPC as a solution to the OC problem. Moreover, it provides the local approximation of the optimal cost-to-go function Z, and thus we are able to evaluate the control Hamiltonian H, which satisfies the Hamilton-Jacobi-Bellman equation. Guided by this MPC solver, we train our policy with MPC-Net. MPC data are generated by sending the robot with different gaits to various targets. These data are pushed into a reply buffer, and batches are drawn from this buffer for the optimization in the policy parameter space. Here, MPC-Net differs from other approaches, as our previous work on MPC-Net showed that minimizing the control Hamiltonian is also a suitable objective for imitation learning. To monitor the training progress, we perform rollouts with the current policy and compute metrics such as the average constraint violation and the survival time. Whenever data are sent to the learner, the current policy is also sent to the data generator, because for the data generation rollouts, the system is actually controlled by a behavioral policy. The parameter alpha linearly decreases from 1 to 0 in the course of the training, and thus we move from off-policy to on-policy data to address a potential mismatch between the distributions of states visited by the optimal and learned policies. Let's continue with some implementation details that are necessary to make this approach work in practice. For the mentioned rollouts, we use the physics engine RISEHim instead of just the kinodynamic model used for MPC. With respect to the data generation rollouts, the availability of more realistic training data improves the sim-to-real transfer. And for the policy evaluation rollouts, we get more accurate metrics of true performance. Instead of expecting the policy to sum or infer a user-defined gait, it is more direct to encode the state of the gait based on the mode schedule and the current time. To this end, we stack the lag phases phi, the time derivatives phi dot, and the phase-based sinusoidal bumps, leading to the so-called generalized time, which by abuse of notation replaces the absolute time in the policy. The plot shows these components during static walk for the left foreleg, which is swinging from 0.3 to 0.6 seconds and otherwise in contact. Especially including phi dot facilitates the learning of sharp changes at mode switches and help to reduce the constraint violation. The user's twist commands are transferred into desired trajectories xd, which should be tracked by the policy. Therefore, again by abuse of notation, we replace the state in the policy with a tracking error called the relative state. The matrix T transforms the pose error from the world into the base frame, which makes training and deployment invariant with respect to the absolute orientation. The relative state improves the usability of MPC-Net policies because now you can freely steer around the robot. An important part of the implementation is the representation of the policy. The multimodal nature of hybrid systems, such as the quadrupedal robot animal, motivates the usage of a mixture of experts neural network architecture. We use 8 MLP experts, which are selected by an MLP gating network. Accordingly, the policy can be written as a weighted sum of expert policies. For the training, we need a loss function, so simply inserting the policy into the Hamiltonian leads to the loss L1. However, this loss results in cooperation rather than competition. Therefore, our previous work on MPC-Net used the loss L2 to encourage specialization, as each expert has to minimize the Hamiltonian individually. Moreover, in this work, we observed that the performance of a policy improves if each expert specializes in controlling exactly one mode of a hybrid system. However, with L2, the policy has trouble to achieve this kind of single responsibility expert selection behavior. Therefore, we introduce a new loss function, which is inspired by the log probability of a Gaussian mixture model. Simply put, the loss is the log sum exponential of the expert's Hamiltonians hi, where beta is an inverse temperature parameter, and the partial derivative of v with respect to t is a bias term motivated by the HJB equation. Note that the Hamiltonian can be seen as a continuous version of the Q function, and then this term has some similarity with the advantage function. Moreover, the expert weight pi can be seen as the prior probability that expert I can minimize the Hamiltonian at the current observation. In that light, we can define the corresponding posterior probability qi, which takes into account how well expert I does relative to the other experts. Then the gradient of L3 can be written as shown, which can be understood better when comparing this to the gradient of L2. For L3, the expert updates are weighted by the posterior instead of the prior. Moreover, the gating updates have different signs. For L3, the expert weight receives a reward according to the ratio of the posterior and prior probabilities, leading to larger updates if an expert is doing better than predicted a priori. In contrast, for L2, the expert weight receives a penalty given by the size of a corresponding Hamiltonian, and all other expert weights increase accordingly. As shown by the table, these properties enable L3 to better achieve the desired single responsibility of the experts for the modes. In particular, for beta equals 1, L3 manages to do so for 100% compared to 40% of the training runs for trot, and for 90% compared to 0% of the training runs for static walk. To see why the single responsibility is indeed advantageous, let's look at these policy evaluation plots for policies trained on static walk with L2 and L3. With L3 and single responsibility, the policy achieves a lower constraint violation during the rollouts, and there is a faster increase in the survival time. Now that we have seen the method and implementation, it is interesting to compare the extended MPC-Net to its MPC teacher and to other imitation learning approaches such as behavioral cloning, where behavioral cloning is commonly used and tries to minimize a distance metric between the teacher's demonstration and the learner's policy output, which is in our case the control input U. As shown by the table, all approaches achieve the maximum survival time of 20 seconds when commanded to walk forward on flat terrain. However, as also shown in the videos, on rough terrain, which was not part of the training data, MPC-Net outperforms behavioral cloning. In addition, compared to real-time MPC, MPC-Net policies achieve similar survival times when commanded to walk forward on rough terrain. Learning from MPC simulated at the high rate of 400 Hz seems to enable the policies to compete with real-time MPC. So far, I have presented results for single-gate policies, so let's look at what we are actually targeting for, that is a multi-gate policy. To this end, the data generation performs pure trot and pure static walk rollouts, and the policy has to learn both gates from these data. These plots show that such a multi-gate policy achieves similar performance like the corresponding single-gate policies in the policy evaluation rollouts. Note that the multi-gate training goes through twice as many iterations, and all policies are trained with L3 and achieve single responsibility of experts for the modes. However, in the more complex multi-gate setting, this single responsibility cannot be achieved reliably, which impedes the learning of high-performing policies. Therefore, influenced by the learning by cheating idea, we introduce a guided loss function to incorporate our domain knowledge that for a hybrid system, the expert selection should be related to the mode selection. To formalize this, let's write the empirical probability to observe mode I as pi tilde. Then the learner can be directed by the guided loss LG, consisting of the already discussed versions of the expert loss LE and of the loss LD, which incorporates the domain knowledge. The parameter lambda controls the relative importance of both loss types. Since matching the modes in experts is essentially a classification problem, a natural choice for LD is the cross-entropy between p tilde and the prior probability distribution predicted by the gating network. However, for L3, one should use the cross-entropy between p tilde and the posterior probability distribution. To see why, note that the gradient of L3 can be also obtained from this expression, where qi bar is equal to qi, but fixed for the moment, and thus no gradient is backpropagated along this variable. The cross-entropy between p tilde and p and the cross-entropy between q bar and p can be in conflict, since both try to pull p towards currently fixed and possibly different distributions. Therefore, since L3 already ensures that p is pulled towards q bar, it is better to pull q towards p tilde. As a result, the guided loss reliably leads to single responsibility of the experts for the modes. Let's see how this new method performs on hardware. What you see is a multi-gate policy trained with the guided version of L3. As intended, a single policy can learn several gaits, such as trot, as shown before, as well as static walk and pose control, as shown next. The robustness in simulation discussed for the benchmarking also transfers to multi-gate policies on hardware. To demonstrate the generalization, we can let the policy alternate between the learned gaits, although this transition was not part of the training data. The bottom figure illustrates the contact pattern for the alternating gait executed in the video. So in conclusion, our extended method and implementation result in improved performance compared to our previous work. We introduced a log partition loss function, which leads to a better expert localization and thus almost always achieves single responsibility for single gate policies. Moreover, our approach enables a single policy to reliably learn multiple gates by the incorporation of domain knowledge through a guided loss function. We also show that MPC-Net policies are comparatively robust. But there are also some limitations to our approach. For example, our performance is naturally limited by that of the MPC teacher. In addition, our policy still requires a predefined mode schedule. However, this could be addressed by learning an observation-based mode selection. Thank you.